So morning. So we'll come back to the Laplace Newtonian potential. So last class we have introduced a proposition where when you can remove a singularity of a harmonic function. So let me go and read a thing and then give you a proof. So this is a removable singularity. Suppose omega is an open set in Rn and x naught belongs to x naught is anything and u is a given harmonic function omega minus x naught, and your ux is in the small order of your fundamental solution. That means the singularity of u is in order smaller than the singularity of the fundamental solution. Then u can be suitably defined at x naught so that u becomes harmonic in omega. So let me give a proof of this theorem. So we will present a proof of removable singularity. Proof of removable singularity. As you see, you can see that's a bit of a tricky proof, but it's not that very difficult, but the proof is difficult. So we give the proof and give the proof. Give the proof when n greater than or equal to 3. That doesn't matter because the form of the fundamental solution is different for n greater than or equal to 3 and n equal to 2. For n equal to 2, use the corresponding fundamental solution. Use the corresponding, then the proof goes exactly. Corresponding fundamental solution. You will see where I am using the fundamental solution. So I want to do this one. Okay. So what do you do there? Let me start with that. So you have a domain here, and you choose an R positive. Choose R positive. Okay. So you have a choose R positive and consider this ball here in such a way that your ball should be the closed ball, so that it is compactly embedded in contained in omega. So you want this one. So this is your R. Okay. So this is your BR, the ball of radius R here. Then I can consider this. We have already used it. I can restrict my U here. So this is your x naught. Okay. So the ball is x naught here, and the U is harmonic. So you see that U is harmonic in, U is given to you BR minus BR of x naught minus x naught, except at that point. But using the boundary values, so you look at U restricted to the boundary of BR, and then you can construct V. How do you construct V? Such that V is harmonic in BR, such that Laplacian of V equal to 0 in BR, and V equal to U. This is a boundary value problem which you have studied already. So this is by Perron's method. By Perron's method. Okay, you can use the Perron's method to solve. Since it is a ball, you can also use the earlier method which we have introduced. So you don't need Perron's method even for the solvability of a ball. We have already solved earlier. Okay, so using the thing. Okay, but like Poisson integral formula. Okay, so you have studied Perron's method or Poisson integral formula. Okay, so you have that already. So define V equal to W equal to U minus V. That's a thing, you can do it. U minus V is harmonic. Now harmonic in, again, u is only harmonic in Br of x naught minus x naught. You see, it's not again because u is not harmonic, and w equal to 0 on the boundary. Okay, that you do. My claim is now, so the claim w identically 0. So w equal to 0 on the boundary. What I am saying is that w equal to 0 not only on the boundary, it is in the except at the wherever it is, because w is not defined at x naught, because there may be a singularity of u, but then it is 0. This requires a proof. I will do that. So the main proof is proving this one. Once if claim is true, you are done now. If claim is true, define w0 at define wx naught is equal to 0, because w is not defined here at x naught. So you can you define u at x naught is equal to v at x naught itself. Okay, that implies u is identically v in Br fully. So I can redefine by my solvability of v. So you can define exactly my u at x naught in Br implies u is harmonic in Br. In Br of x naught. So you have to give the proof of w equal to 0. So it remains to show your w equal to 0 in that. So the proof of the claim. That's what technical. Okay, proof of claim. So you are using whatever you have studied so far here. So as I said, we are assuming n greater than or equal to 0. So far we have not used that one. So assume n greater than or equal to 3. Okay. So now I define for n greater than or equal to 3. I define something like two function z plus or minus x is equal to, choose epsilon positive, arbitrary, small. Eventually this will become small. So choose epsilon greater than 0 and you define epsilon equal to modulus of x minus x naught power 2 minus n minus plus or minus w of x. It's the same w of x. So here you see, this is the part of fundamentals except for the constant. So you don't have to include constant here. This is part of fundamental solution. Part of fundamental solution. That's the main singularity part of the fundamental solution. Whether you put constant or not, it doesn't matter. So in the case of n equal to 2, 3, you have to work with the log mod x minus x naught. That's all the difference here. Okay. Then this is a harmonic. This is, you know that is what it makes. This is harmonic in Br minus x naught. You see, except that deleted neighborhood, deleted ball, it is harmonic. Similarly w, so that implies z plus, when you use plus here, minus here, minus here. Okay, so that means z plus or minus, both functions are harmonic. Harmonic in Br minus x naught. Okay. So now we have to play little more game. So let's look at the boundary. Okay. So let's look at the boundary. Suppose x is in boundary of Br. If x is on the boundary of Br, what happened to z plus or minus x? X minus x naught is r. So this is epsilon power r power 2 minus n. But w is 0 on the boundary. Okay. Since w of x equal to 0 on the boundary. So you have epsilon power 2 minus n, and that's positive. This is a positive quantity. So on the boundary you have a harmonic function, not fully. So you can apply maximum principle, etc., but you can't immediately apply maximum principle because z plus is minus or harmonic inside is not given. But you can take an annulus now. So if you have a ball here, this itself is in a bigger domain. So you can think, and then this is your R, this is your X naught. So I can construct a ball here, any ball here, you like it. Okay, eventually you can choose, you are interested in only near the neighborhood of X. So eventually R will be also small. So I can choose a neighborhood here, rho, any rho. So you can choose R greater than rho, greater than 0. Okay, and then you can actually show that Ux, so you look at on the boundary of that one. So X is in the boundary. So if I choose X is, so you know that this case, this is the one, the boundary. If X is on the boundary of B rho, then this will be, then what is your Z plus or minus X? Then Z plus or minus X, then Z plus or minus X is equal to epsilon, you will get it epsilon rho power 2 minus n. Instead of R on the boundary, again X minus X naught, and plus or minus W of X. Okay, so now look at these things. So this is where you are coming. Here Wx is U minus V. And V is a bounded quantity. And this singularity, this is something order of mod X minus, order of singularity of phi X minus X naught. Small order. So for R small, so you choose R small. If you write down this thing, so and X is on the boundary, this will become epsilon power rho power 2 minus n. And this singularity is small order of rho power 2 minus n. So that immediately tells you that if you have this quantity, you see this is rho 2 power n minus 1 and this is small order of 2 power n minus 1. That means this will dominate as rho tends to small, or rho becomes smaller, R becomes smaller, rho becomes smaller, and this will, rho will dominate then the second term, then this term. That means this will be a bigger quantity. As rho becomes, R becomes small, rho becomes small, this will become small quantity, then this, the irrespective of plus or minus there, that will immediately imply your Z plus or, see, you see why beautiful way of applying your theorems. So this will be greater than 0 for greater than 0 on BR of 0 also, on this boundary also. So on both boundaries, this boundary you already got on the boundary of BR, you got this one positive, and on this boundary also. So if you have two domains here, and so you have a Laplacian, so this is a boundary, this is positive, so this is boundary is also you are, so on this domain your Z plus or minus is an okay, harmonic. So you see, so you have a harmonic function in an annulus whose boundary values are positive. So that will immediately, by maximum principle and other things, you will immediately get that your Z plus or minus is strictly positive in the annulus. So you get that in the annulus R greater than mod X minus X naught. This is annulus. This is what the derivation. You see, so you have a beautiful way of deriving that it is positive, plus or minus is positive on this annulus. Now we will complete the proof chosen. Now you want to show that W is equal to 0. So you don't forget your aim. So you want to prove that W equal to 0. So in other words, you want to show that W equal to 0. So our aim is to prove. So that please recall once again. Our aim is to show W of x1 equal to 0, W of x1 equal to 0 for all x1 in BR minus x0. So fix x1, any x1. So fix x1 in this annular. So you have so you have here, and then you have x1 here. You choose x1 here. R is already chosen by small, satisfying the earlier thing. So you can choose R small enough you like it. And then if you have an x1, so it's not x1 is different from x0. So there will be a distance. So you choose your row in this way. So choose row such that, okay, x1 is in that annulus, x7 belongs to the annulus, x1 belongs to the annulus. Annulus. What is annulus? R greater than mod x minus x0. That's greater than rho. And so that implies your wx1 here. So you have your z plus or minus x is positive, and what is w? Z plus or minus. So you recall this now. You see? So use this. This is positive, and this so this can be estimated by this one immediately. So if I go there, so use that. So that implies immediately, if I compute my modulus of wx1, I can estimate that's equal to plus or minus, doesn't matter which sign it is. That's what either plus or minus, doesn't matter, and that will be less than or epsilon, because it's positive. X1 minus x0. X1 belongs to there. X1 minus x0 power 2 minus a. X1 is fixed. X1. Now as epsilon is arbitrary, implies my wx1 is equal to 0, and that implies w is identically 0 in br of x0 minus x0. And then we already seen that if that's the case, we concluded the claim. If w equal to 0, then I can define w of x0 equal to 0 and ux0 equal to vx0, and you can x0 0. Okay, so that's important proof of this. And now what we will do, we will construct an example of a continuous function example. That's what we are going to do. Example, a continuous f such that minus Laplacian equal to f has no classical solution, has no C2 solution. That's what we said in the beginning, okay, or in the previous class. So we will do that now. Okay, so that I will not do all the constructions, but so I request you to do it. So consider a ball of radius r. So we are giving just an example, counter example, 0 in R2. Okay, where 0 may be less than r, so you can use it less than 1. You use that r less than 1. Okay, and define u by u by u of x. This is some formula, so I will write it u in x1 x2. So do these computations. It's chosen very cleverly. x1 square, and do the computation so that there are no error that I am writing here, into minus log mod x. So x is less than 1 because it's in the ball of radius less than 1. So this will be negative. So that's why I put a negative sign here, is equal to half. Okay. So you will see there is a singularity here, but there is smallness here. So this is a continuous function. Is a continuous function. If you know that, even if the log mod, if you put some power, anything x power, it will become continuous. Okay. So the singularity of logarithmic singularity is smaller than this kind of x, whatever power of x, whatever power, any small thing. For example, x log mod x goes to, log mod x goes to infinite minus infinity, but x log mod x goes to 0. So you know such kind of things. Okay. Any power x log x goes to 0 as x decreases. You know this. Or any power here if you take it. Okay, positive power, you take it. Okay, of course, negative power, it will be full of singularity. So it is continuous. You can check it. So do these verifications. I'm not going to do all the verifications here. Okay, and then you compute. Then you can actually. So the singularity is there. Otherwise, these are all very nice functions, including thing. So that then you can compute. Then you compute this one. U is in. So the continuity is there everywhere, but you don't have much differentiability. But you can solve, but you have C infinity inside. PR, you can go up to B, any boundary. So the singularity is only at the origin. Okay. So you can have the differentiability, but when you differentiate further, you don't get the derivative is continuous because it will produce more singularities. So the only at the continuity level you have it. So see, u is in continuity, you have up to the thing. You have that there is no problem. Okay. So you can differentiate this one, and then of course, in general, when you differentiate, you don't get continuity, but this example is in such a way constructed, the Laplacian of u, some of the singularities will get cancelled, and you can compute. So I will leave this thing, compute Laplacian of u. Okay. So I'm not saying that first derivative or second derivatives will be continuous, but you can compute Laplacian of u thing. So let me write down x2 square minus x1 square. So let me write down the thing, 2 mod x square. Please do the computation so that there are no mistakes whatever I have written. N plus 2, because this is computer, but I hope there won't be any error, but still check it. Log mod x power half, this is square root of that, so half plus 1 by 2 times minus log mod x over half. Okay. So the interesting thing is I define this to be my f of x1, x2. So though the derivatives need not be continuous, but I am saying that this Laplacian is a continuous function. I have not defined this one. This is defined for compute for x1 or x2 not equal to 0, 0. So I have computed only that one, but because I know that the derivatives are can define because that's singularities, so I can do only at that point. But what is interesting is that then by defining, so you can verify that this has a limit basically. By defining f0, 0 equal to 0, we can see that. So I will leave these computations to you. We can see that f is a continuous function So our analysis is not over, continuous in BR of 0. So you have a function. Okay. What about u? Whether u is we said it's only continuous. We don't know about its derivative, whether first derivative, second derivatives are all continuous, but that's not true. It is discontinuous. So only you get for the Laplacian, and you can do also show that. Okay, so I will leave that also to you. Show that you compute the only one. So this is a kind of cancellations may be taking place. If you compute your dx1 square, and if you take your limit mod x tends to 0, you can show that this is equal to plus infinity. Therefore, that gives you that you have, therefore u is not a classical solution, is not a classical solution of Laplacian u equal to f. But this does not contradict here. Only the u you have constructed with that f is not classical. But what about, does it have any other classical solution? So the claim is that Laplacian there does not exist any classical solution v. That's the thing. Any classical, not just u. There does not exist any classical solution v such that Laplacian v equal to f. How do you prove this one? And this we assume. If not, so this is by contradiction. If not, assume there exists v a C2 function, C2 of BR of 0, of course, such that Laplacian of v equal to f. Then define your w equal to u minus v. Okay. So if you define w equal to v, u is then implies Laplacian, because Laplacian u equal to f, Laplacian v equal to f, and in where in the inside thing. So v is harmonic in BR of x naught minus x naught. So you see, and then u is a, you look at here, u is a, because there is a limit here, z as x tends to is a continuous function. You can define extend the continuity. That's what we have done. That it's a continuous function. Again, u0 0 is also defined. U is a continuous function. Since u is continuous, there is no singularity at all. This is a bounded function. So no singularity at all. Bounded. This is also bounded because it's harmonic given. Hence no singularity. No singularity. That immediately implies it is much nicer function. So it is there is no singularity. So definitely it will be like this, x minus x naught. Okay. So I said you can even allow some singularities. There is no singularity here. So apply previous proposition to w, not to u. Previous proposition, the proposition we have just now proved, to proposition to w, okay, to extend, to define, application to w to define w0, you can extend that as a 0 function. So you can define w to be a 0 function. So that implies as a harmonic function, you don't even have to be, so I don't say that w equal to 0. You can extend to define w as a harmonic function. You can extend, suitably define harmonic function in Br of x0. Br of 0 rather. So I am taking everything 0. 0, Br of 0. Okay. Or there is no x0 here. x0 is 0 here. So x0 is 0 here. So no problem. So you have you can define here of 0. So W is harmonic. V is already constructed as harmonic function. R harmonic in Pr of 0. That implies U equal to U, W is equal to U minus V. So U is equal to W plus V is harmonic, which is a contradiction, which we already thought harmonic in Br of 0. Okay, which is a contradiction because we already showed that U is not a classical solution. So U is not C2. So you see, U is not a C2 function, and you cannot do that one. So it shows that is a W. In fact, it's a C2 function which you are showing it. It is basically a it's not harmonic. So I have mentioned something there. Only W is harmonic. So what I stated is wrong. Okay. What do you know that W is harmonic? V is not harmonic. So that's why I made a mistake. Okay. W is harmonic, but V is smooth, harmonic in V, and V is smooth, C2. Okay. So therefore, W is harmonic, hence it is C2. V is C2, but V is not harmonic. So that W is smooth, V is smooth, and you need only this one. It is smooth in, so it's not harmonic. Sorry for the mistake. Okay. Which is the contradiction? It's not harmonicity. Laplacian V is not given to be harmonic because V is a solution to Laplacian of V equal to F. Similarly, U is not harmonic because of Laplacian. So, but you show that this is a harmonic function which W is harmonic. So you have this C2. So the essentially shows that there are continuous functions for which your Laplacian of U equal to F is not solvable. So that's, and C1, so what we are going to show in the next class to begin with, next we show when F is in C1 of omega bar, then Laplacian of U equal to F is solvable. First we will show this, and then we will develop our analysis for the solvable classically. Okay. So I'll stop here now. Thank you very much.